So, in the last lecture we talked about thermonuclear fusion, and we discussed that the most important parameter is reaction rate, that is how many fusion reactions take place per unit volume per unit time if a particular plasma concentration is confined in a certain volume at a certain temperature. And I gave you an expression and promised that I will justify it in this lecture, and the expression was that reaction rate would be something like the concentration of the two interacting species and then average value of sigma v. So, this is reaction rate. Nx and y, x and y are the two nuclear species which are fusing, which are doing that fusion reaction. So, x plus y is going to z and possibly some other particle, gamma particle or a small nucleon or something. So, this x and y and this nx and y are the concentrations, that means number of nuclei, number of x nuclei per unit volume, and similarly this ny is number of y nuclei per unit volume. Sigma is the cross section, sigma is cross section for that particular reaction. Roughly speaking, sigma you can take as an area presented by x nucleus, and if this y nucleus hits that area, the fusion reaction takes place. That is how we define cross section. You remember, cross section is in units of centimeter square, it is an area unit. So, if you have a nucleus x and another nucleus y here, and if they are coming towards each other, you can take x relative to x, y is coming, and then this x, mentally you think that there is an area, this area surrounding this x nucleus, and if this y hits somewhere in this area, the reaction will take place. So, that is how the cross section is geometrically conceived. So, that is the sigma, and v is the relative speed. The two nuclei x and y are approaching each other, and the relative speed, the speed of y with respect to x or of x with respect to y, that is this v. So, first let me see how it is proportional to v, right. Sigma is of course is directly related to the probability of that fusion reaction. So, if sigma is large, the rate will be large, if sigma is small, the rate will be small, and for all these fusion reactions this cross section is very, very small. So, that sigma is there. V, let us look at this v. First consider a nuclear, say scattering, right, scattering, a nuclear reaction say scattering. So, if you have a target, normally in a scattering geometry you have a target fixed, and then a beam of these projectile nuclei or ions, they come. So, these are nuclei, let us call them y nuclei, and in this target you have x nuclei, these are x nuclei here, this thickness you take as d, the beam diameter you take as some capital A. So, how many scattering will take place per unit time? So, for that how we make the calculation? We consider a particular nucleus x here, a particular nucleus x here. So, what which nuclei will scatter from this nucleus. So, the cross section comes into picture. If the cross section is sigma, then you make an area here, this area is sigma around this X nucleus. This X nucleus is writing here, zoomed version because the cross sectional areas are very small as compared to any target in the laboratory. So, that is sigma. Now, this beam is coming, So, if the velocity here is v, if all these nuclei in the beam, they are coming with velocity v, and I want how many of these y nuclei are hitting this area in some time interval dt. So, what I can do? I can construct a cylinder here, mentally construct a cylinder here with one face at sigma, other face parallel to it, and length of the cylinder v into dt. So, at any time t, at any instant, whatever y nuclei are here, whatever y nuclei are inside this volume, they will hit this area. Anything behind this will not be able to reach this sigma in next time interval dt, and anything inside it will certainly hit this, because this length is v dt, nuclei moves a distance of v dt. So, the nuclei which are here on this face, they will also reach this sigma, and all the nuclei ahead of them, they will certainly reach this sigma, and anything behind will not. So, how many nuclei are there in this volume? So, if the concentration is n, concentration of y nuclei in the beam. So, per unit volume of the beam, if there are small n y nuclei, then the number of this scattering or reaction in time interval dt that will be small n into sigma into v into dt. Sigma into v into dt, this is the volume, sigma is this area, v dt is this length. So, sigma into v into dt is this volume, n is the number of y nuclei at any instant per unit volume in the beam. So, this is the number of nuclei at a particular instant in this volume, and hence in time dt these many scatterings will take place, or whatever nuclear reaction will take place, and therefore, the rate, the reaction rate will be proportional to the concentration and sigma and v. So, that sigma v essentially comes from this. Now, in the thermonuclear fusion, the case is slightly different from this. You do not have a solid target. It is a volume in which you have both the x and y nuclei in gaseous form, in plasma form. You have electrons, you have these positive nuclei, and they are all moving in random directions and with random speeds. So, not like a beam coming in a particular well defined direction, but essentially this essential idea remains there, and finally, you get that sigma v terms there also. What I can do here is, once again in the gas, now in this thermonuclear plasma you have a volume, and in that volume you have a gas in which these x nuclei are there, y nuclei are there, electrons are there, are all moving, but still you can consider x nuclei here, and relative to this you can look at the velocities of the y nuclei. So, if I use relative velocity in place of v, and then look at the group of nuclei, y nuclei, which are coming towards this nucleus from a particular direction. So, consider those nuclei which are coming towards x in this direction. So, this situation is very close to that situation. The directions are different, that is okay, but if the nuclei are coming from some other directions, so for this direction you will construct a sigma and then see that how many are going through this. If you have some other kind of other group of molecules or nuclei, you consider this the same nucleus X here, you construct sigma this way. So, sigma as such, the cross section as such is only the magnitude of that area presented by the nucleus. So, if the projectile nuclei are coming from this direction, the area is to be constructed this way. If the projectile nuclei are coming from top, the area sigma is to be constructed this way. So, for each group one can do this. So, that is how they resemble. Another difference would be that in a scattering experiment, the same nucleus X can scatter the many of the incoming particles, but in fusion reaction, if one fusion has taken place, that particular nucleus is consumed. It is only the other X which can come. So, all those things will be there, but that expression into V will be there. You can think of a particle X here, and then you can ask, okay, I construct this sigma into V dt volume. So, this V dt is length. Now, generally the concentrations are low, sigma is extremely small. So, there is hardly one nucleus Y here, in a typical case. So, the reaction rate will be proportional to the probability that you have a Y nucleus here, and that probability will be proportional to this V, because if you take larger volume for same dt, larger volume, the probability of finding a particle Y here will be larger. So, the probability in next dt there will be a fusion with this X is again proportional to this V, and of course, proportional to sigma, and therefore, it is sigma into V that comes into picture. So, that is how this sigma V comes here, and of course, the concentrations of X nuclei and Y nuclei, it has to be proportional to that. In fact, this gives you the number of pairs of X Y which can fuse per unit volume. So, it is this. Now, what is this average business? Why I am putting these angular brackets here? These angular brackets denote that we have to average over different velocities, because in this gaseous plasma the nuclei are moving with random speeds, as we discussed earlier also. You can assume Maxwell-Boltzmann distribution. So, you will have different values of relative speed V. Sigma will be same for the same kind of fusion in the similar at the same temperature and velocities and all that, but then the particles will be moving with different velocities, and hence an average is needed over these different velocities. What velocities are these? These are relative velocities of Y nuclei with respect to X nuclei, or of X nuclei with respect to Y nuclei. And I have put sigma also inside the angular brackets. This is because sigma also depends on velocity, and the dependence of sigma, dependence of cross section of fusion on velocity of relative velocity of these two particles which are trying to fuse with each other, has two components. One is of course, as we had discussed from the very beginning, that these fusion reactions, they have to go through a barrier penetration process, because when two nuclei are fusing, you have two positively charged particles coming very close to each other. So, when they are coming closer to each other, then the Coulomb potential energy is increasing, and when they come into this nuclear range, so that the nuclei are now ready to fuse, they are just penetrating each other, then the nuclear potential will take place. So, you have a potential barrier, and the probability that this barrier will be penetrated depends on that relative velocity. and that expression is barrier penetration probability that expression is like e to the power minus 2g, where 2g is written for z1 z2 e square over 4 pi epsilon naught and then 2 pi by h cross v. So, the relative speed comes here, the barrier, as you remember, it is something of this sort, there is a Coulomb type of potential, and then here it nuclear thing takes place and potential is like this. So, this is V and this is R separation, and the energy, that is the kinetic energy of the particles before the fusion when they are widely separated. So, that kinetic energy, and this is the barrier that they have to penetrate and then come into this nuclear range. So, if the relative speed is high, that means the kinetic energy of these initial kinetic energy of the particle is high, and this dotted line will go up, and therefore, the probability of penetration will increase. So, that is how this penetration probability depends on V, and the cross section, which is again some kind of probability of fusion, right. So, that is directly proportional to this barrier penetration probability. If the barrier penetration probability is high, then the fusion probability is also high, the cross section is also high. So, sigma will have a factor of e to the power minus 2g because of this barrier penetration coming in. But this is not the only velocity dependence. One thing is that this is an approximate expression, and this is valid only if this available energy is much smaller than the height of the barrier, or if this range is very high. That means, if the barrier penetration probability itself is very low, then you use this expression, and that is the case in any thermonuclear reactor one tries to design, or that is there in the stars. Now, another dependence is, apart from this barrier penetration and Coulomb potential and all that, for low energies, any nuclear reaction, there you have a velocity dependence, and that velocity dependence is proportional to 1 by v square. So, I will justify that also. So, suppose you have a nucleus x here and nucleus y here, and this y is going with velocity v, mass of this y is, let us say, m. Now, we are talking of nuclear reactions in general, at low energies. So, again I will be using lots of classical, lots of semi classical geometrical pictures and so on. So, suppose it is coming like this, and this impact parameter, this distance, this is the line of motion, and here is that nucleus towards which it is coming. You can take the relative velocity, and this distance is the impact parameter, call it b, small b. So, the angular momentum is m into v into b, this is b. That is the angular momentum. Classically, this b can vary continuously, and therefore, angular momentum can take any value. But if I bringing some quantum mechanical picture, the angular momentum has to be quantized. In any direction, it is some integral multiple of h cross. So, if I construct a circle here around this x of radius b, these nuclei can come from any side of the nucleus. If they are hitting here impact parameter B, then they can fall anywhere on this circle. So, all nuclei y which are falling on this circle will have this angular momentum. And if I say that it is integral multiple of h cross, say L into h cross, if I call this as, let us put B L and call it L into h cross, then this B L should be equal to L h cross by m v. The nuclei y which are coming with the same velocity from the same direction, but with a different impact parameter corresponding to the next unit of angular momentum L plus 1 times h cross. For them this impact parameter will be B L plus 1, that will be L plus 1 times h cross by m v. What happens? So, these are the nuclei which are coming like this. So, this corresponds to, let us say, L h cross, this corresponds to L plus 1 h cross. For them this B here will be given by this. What about the nuclei which are coming with distances which is between this B L and B L plus 1? So, let us say that all these nuclei will be clubbed with this B L. So, any nucleus which is giving you angular momentum less than L plus 1 h cross, but more than L h cross, let us club that all with L h cross. So, that we are quantizing this classical continuous quantity. So, all these nuclei will be taken as corresponding to angular momentum L h cross. Then from L plus 1 to L plus 2 here, all these nuclei will be considered to have angular momentum L plus 1 h cross and so on. So, now let us calculate number or area presented by the X nucleus for nuclear reaction with angular momentum L h cross. How much is the area presented here? So, if you have this nucleus X here and this is B L and draw a circle, and then B L plus 1 draw another circle, this area, any Y nucleus falling on this area, any Y nucleus falling on this area will have impact parameter more than B L, less than B L plus 1, and all those Y nuclei will be considered to have angular momentum L h cross. So, the area around this X which admits this angular momentum L h cross is this shaded area between B L and B L plus 1, and that area is pi times B L plus 1 square minus pi times B L square, and that is equal to pi B L plus 1 square is here. So, L plus 1 h cross by L plus 1 h cross by m v, mass times that relative velocity. This mass is also reduced mass. So, this whole square and minus L h cross by m v square. and we can further simplify it. Pi here, h cross square m square v square here. So, I have taken h cross square m square v square out, h cross square m square v square out. It is L plus 1 square minus L square, which will be 2 L plus 1. So, it is 2 L plus 1. So, the area presented by this X nucleus for nuclear reaction with angular momentum LH cross is this. So, starting from L equal to 0, how much is the area presented for L equal to 0, for L equal to 1, for L equal to 2, and so on up to some maximum L max. What is that maximum L? Maximum L is given by the nuclear range. These two nuclei are coming and they are interacting through nuclear forces. So, you have a nuclear range for that, capital R. If the distance, the lowest distance between the particles is more than that, then there are no nuclear interactions. So, the maximum impact parameter which are allowed for these two particles to come within a nuclear range and therefore interact through nuclear potentials is that capital R. So, m into v into this should be equal to L max times h cross. Once the impact parameter has become capital R, that is the maximum you can take. If impact parameter is more than this capital R, then they are never in nuclear range and no nuclear reaction will take place. So, the maximum value of this L max is given by this equation, m into v into capital R is equal to L max into h cross. This capital R here is the nuclear range, nuclear interaction range. So, up to this L max, if I consider starting from 0, what I get is the total area presented by this nucleus for nuclear reaction, and that is the total cross section for this reaction. So, the cross section is equal to summation L going from 0 to L max and then this quantity pi h cross square by m square v square 2 L plus 1. Okay, that is the total area presented by the nucleus for nuclear reaction with different values of L starting from L equal to 0 to L max, and this quantity is pi h cross square m square v square, and this is just an arithmetic progression, arithmetic series 2 L plus 1, L equal to 0. So, it starts with 1, 1 plus 3 plus 5 plus 7 and so on, sum of all odd numbers. In how many terms are there? 0 to L max. So, L max plus 1 terms are there. So, summation will be L max plus 1 by 2, total number of terms by 2, and then first term plus last term. First term will be just 1 and the last term will be 2 L max plus 1, using the equation for summation of a arithmetic series. So, 2 you can cancel and it will be L max plus 1 square. So, this is equal to pi h cross square m square v square and then L max plus 1 square, and that is pi h cross square by m square v square. L max is here. Where is L max? L max is given by this. So, L max is m v capital R by h cross. So, it is L max is m v capital R by h cross. This is L max and plus 1 square. If you take h cross square by m square v square inside this bracket, it will be pi, and if I take it inside, it is h cross by m v, h cross by m v. So, this will cancel, this will be r and plus h cross by m v whole square. Now, estimate the two terms capital R and h cross by m v for a typical case where the plasma is going through this thermonuclear fusion. So, h cross by m v, h cross by m v, you can take square of this. So, square of this will be h cross square m square v square m v square, let me write this way, and multiply by c square here and c square here. Now, h cross c roughly 200 mega electron volt femtometer. So, this is 200 into 200 MEV square FM square divided by mass into C square MC square. So, if I take typically let us say DD reaction, deuteron reaction, 2H reaction, this is deuteron, so it is called DD reaction. So, the mass here is 2 times mass of proton approximately, and here 2 times mass of proton, and therefore, the reduced mass will be just MP, mass of proton. So, mass of proton into C square is 939 mega electron volts, take 1000 mega electron volts. So, MC square is 1000 MeV. Then m into v square, this v is the relative speed. So, mv square, half mv square is the kinetic energy, and that kinetic energy depends on temperature 3 by 2 kT for 10 to the power 7 Kelvin or so. For protons it will be like 1 keV, 1 kilo electron volt, and typically people try to work at few kilo electron volt, because one has to raise the temperature to 10 power 7, 10 power 8 range. So, if I take this mv square as 1 keV, kilo electron volt, so this is keV, 1 keV. So, this will be, so 2 zeros here, 1 zeros here, that will cancel with this, MEV goes with MEV, 1 MEV here, and that MEV by KV is 10 to the power 3. So, it is 40 into 10 to the power 3. So, 40 into 10 to the power 3 FM square, femtometer square. So, this is 200 femtometers. That is just an estimate, typical estimates. So, 200 femtometer here could be 100 femtometer or 50 femtometer or 60 femtometer or 150 femtometers. That is H cross by mv. This is H cross by mv, right. This I had calculated H cross by mv square. I have taken square root here. So, H cross by mv is this, and R, capital R, is the range of nuclear interaction, which is typically say 2 femtometers. range of interaction of nuclei. So, typically 2 femtometers, here it is 200 femtometers. So, this term dominates over that capital R, and therefore, you can write sigma for low energies, right. This m v is low, this velocity here I have taken it 1 keV. So, for low energies this R can be neglected, and then this will be pi h cross square over m square and v square. So, you can see that it is proportional to 1 by v square. So, the cross section, because of this nuclear interactions, goes as this at low energies, and this is much larger than this pi into capital R square, which classically you can think of, that if the range of interaction is capital R, then it is presenting an area pi into capital R square. Anything falling beyond that does not interact with this, anything falling inside interacts, and therefore, the cross section should be pi into capital R square. This line of argument is also okay, but what happens at low energies is that the Y nucleus which is coming with this low energy is not just a very small point particle, it has its own de Broglie wavelength, and that de Broglie wavelength is large. So, even though the center, that Y nucleus, the line I draw, could be beyond capital R, but because of the spread in de Broglie wave, it will interact with the nucleus and the cross section will become larger. So, that is the physical picture. So, the cross section therefore, has two factors. One is this 1 by v square, say pi h cross square by m square v square. Do not go on the exact expression, the important thing that it is 1 by v square, something constant multiplied by 1 by v square, and then e to the power minus 2 g, and g itself contains velocity. Remember, 2 g is z1 z2 e square by 4 pi epsilon naught, and then 2 pi over h cross v. So, that is how sigma depends on velocity, and therefore, when we average this expression for reaction rate, sigma also goes inside that angular bracket, sigma v n x n y, that is reaction rate. All right. So, how does one calculate this average of sigma v? This average of sigma v, remember, velocity v, relative velocity v has a Maxwellian distribution, and that is why this averaging is needed, and that distribution is probability or fraction of particles with speed between v and v plus dv, can call it PV dV. You can take it as a fraction of the total particles which is having this velocity, or here fraction of the total pairs which are having this relative velocity between v and v plus dv. So, this is given by that Maxwell-Boltzmann distribution 2 by pi half m by kt 3 by 2, then v square e power minus half m v square by kt and dv. So, sigma v, average value of sigma v will be integration v going from 0 to infinity, and then sigma into v, and sigma we have seen it is some constant divided by v square, and then e to the power minus that z1 z2 e square by 4 pi epsilon naught 2 pi over h cross v, that is sigma. The sigma is this expression, and then into v, sigma into v, and into this fraction p v d v, that is all this constant. I am interested in temperature. So, all that constant can go here, but that 1 by t to the power 3 by 2, that I would like to keep. So, 1 by t to the power 3 by 2, that I would like to keep here. All other things go into this constant, and then you have this v square here and e power minus half m v square by k t and d v. This v square can be cancelled with this v square, and this v remains in numerator. So, you can define, or you can work with this E equal to half m v square, right. This E is that kinetic energy, thermal kinetic energy. So, E is half m v square. For different pairs you have different values of relative speed v, and therefore, different values of E. Here we are averaging over v, here we will be averaging over E. So, if I use this, then in terms of this, if it d E will be equal to m times v d v. So, this v d v, that we can write as d E by m. d E is 2 cancels here, m v d v. So, for v d v we will put this d E by m, and these expression we can write in terms of E. Here it is already half m v square. So, it will be just capital E, and this expression, that this v has to be converted, and let me do that. This is z 1 z 2 E square by 4 pi epsilon naught, and then 2 pi over h cross times v, and v is from here, what is v? V is square root of 2 times E over m. So, this v will be putting here. In place of v, we write square root of 2, square root of E and square root of m, and this whole thing I can write as a divided by square root of E, where a is written for everything except this root E, that is z 1 z 2 E square by 4 pi epsilon naught h cross, 1 square root of 2 here, and then 2 pi here and square root of m here. This whole thing is written as a, then it is a by square root of E. So, the sigma v is equal to integration. The limits for capital E are also 0 to infinity. V, relative velocity v, that goes from 0 to infinity, and E is half m v square. So, the limits also go for E also go 0 to infinity. So, 0 to infinity, 0 to infinity. Then you have 1 by t to the power 3 by 2 c. You can write this as, you can write it outside also, c divided by t 3 by 2. Temperature, it is same for all pairs. So, this, then e to the power minus a by square root of E, that is here, e to the power minus, this whole thing is a to the power a divided by square root of E, this whole thing is e to the power minus capital E by k t, and then v d v is just d E by m. So, d E here, m I am not putting, gets absorbed into this c here. So, this is the expression, c by t 3 by 2 and 0 to infinity e to the power minus a divided by square root of E and plus E divided by capital T, k t. dE. Now, there is a catch. The barrier penetration probability I am using as e to the power minus 2 capital G. And this expression I said is a good approximation only if the kinetic energy of these particles, initial kinetic energy of these particles is small as compared to the barrier height. Barrier height is typically in mega electron volts, and the kinetic energy, the average kinetic energy I said is typically between 1 and 10 kilo electron volts, and therefore, that expression was used for barrier penetration probability. But now, I am taking care of that Maxwellian tail, I am taking care of that Maxwellian distribution, and therefore, I am integrating from 0 to infinity, capital E going from 0 to infinity, the initial kinetic energy going from 0 to infinity. So, we are taking care of all that large speed pairs also, even though the average kinetic energy remains few kilo electron volts. So, in this full integration range, capital E going from 0 to infinity, should I use this expression for barrier penetration probability? Because for large values of capital E which are involved here, this expression will not be valid, but it does work. Why? We will see on our Excel sheet on the computer. What I will be doing? I will show you separately how this factor changes as E goes from 0 to infinity, and how this factor changes as E goes from 0 to infinity, and how the product changes as E goes from 0 to infinity. So, let us go to the Excel sheet. So, here is an Excel sheet. I hope you are able to see this small a is here, and the numbers I have calculated and put some reasonable feasible numbers. This small a, you remember, it comes from the expression e to the power minus small a by square root of E. So, that small a is here, k T is here, and then E is variable, capital E, the energy is variable, that goes from 0 to infinity. So, E by k T I am taking 0.5, 1, 1.5 and so on, and it goes to large values up to 28. I have taken 28 times k T, up to there I have gone. So, A is there, k T is there, E is there. Then I am calculating here this e to the power minus a by square root of capital E. You can see here R T E, it is written, R T is for square root. So, this column, this whole column is for e to the power minus a by square root of E, the first factor in our expression. And then we have the second factor, e to the power minus capital E by k T. So, that is this column. So, we have calculated for each energy, these are the different energies I am considering at an interval of 0.5 k T. So, at each of these energy we are calculating this e to the power minus a by square root of E, e to the power minus E by k T, and then the product of the two terms are in this column. Okay. And then we are plotting this product of the two factors as a function of this capital E in units of k T. So, essentially what we are plotting is E by k T on the x axis, this E by k T on the x axis, and correspondingly the integrand here, then the thing which we have to integrate, that we are plotting. So, if you look at the plot is already here. This is you can see the red line here and a blue line here, hardly visible. This red line is for e to the power minus capital E by k T, it decreases, as this way exponentially decreases, and then this blue line which is almost coincident with the x axis, because at the scales which are given on y axis 0.01, 0.015, on this scale the second factor is very small and it is not visible here. In the lower graph here is the product. So, we are showing you as a function of E by kt the two factors separately on the upper graph and then the product on the lower graph. So, what you see is this product go through a maximum and then again it decreases and becomes very small later on. The scale here you may not be able to see, the scale here is 5 into 10 to the power minus 19. So, for this lower curve do not get misguided by the large height that is being shown here. This is 10 to the power minus 19 scale and here it is 10 to the power minus 2 scale. So, as compared to the scale here, y axis scale here, the y scale here is 16 orders less, but in that it goes through a maximum and then it becomes very small. So, let me change the kinetic energies kT little bit, temperature little bit and see what happens. From 1 let us go to 5 or 4. So, I am putting 4 here. So, now kT is 4 and see what happens, not much visible. So, let us go for 6, what happens. Now, you can see this blue line coming up on this curve here, upper curve, this blue line is coming up at 6 kT is equal to 6 kilo electron volt. The factor, the barrier penetration factor e to the power minus a by square root of capital E, that is started showing up on this scale. So, the red curve drops whereas the blue curve rises as you go for higher and higher value of E, and then the product comes from somewhere this area where the two have some appreciable value. Beyond that the red line goes to almost 0 and therefore, the product is almost 0 here, and before that the red line is there, but then the blue line is almost at 0 level and so the product is almost 0 here. So, if you look at the lower curve and here of course, the scale is also now it is 10 to the power minus 12. So, when I increase this kT from 1 keV to 6 keV, all this product has increased from minus 19 order to minus 12 order. So, the total area has increased here. The total area is also shown here. The total area is obtained by just adding all these product terms and properly multiplying by some factors. So, the area number in number numerical value is given here. If you go slightly beyond say 7 keV, see what happens. So, you can see that barrier penetration probability here has increased considerably and the product here is also increased. It was 10 power minus 10 here, now it is 10 to power minus 9. So, it has increased, this scale is increased. So, the important part is that the integrand, it really does not go to up to infinity, that integrand becomes quite small once you have say in this particular diagram 15 keV or E by kT equal to 15, more than 15, the product goes to very small values. So, this is how the thing goes. Now, I will just show one more thing. Suppose I increase kinetic energy and see what happens. Look at the kinetic energy here, kT here, and the value of this integral, the whole integral sigma v integral. So, let me zoom it slightly more and then I will change this value of kT and look at this, this is the integral. So, look at this, from 7 I am going to 100, the number was 10 to the power minus 9 and see what happens, it becomes how much, 10 to the power minus 4 or so. So, increased, go beyond 1000, further increase 0.002, see the value here, this is 0.002, further increase 10,000, from 0.0028, 0.0056 increasing, go for 50,000. This is 0.0056 at present and it is 0.0043. So, it has decreased. Go for 100,000, from 0.004 it has become 0.003. So, this integration, if you go to very high temperatures, then this integration, the value of sigma v will again start decreasing. Initially it increases at 1 keV, now it is 1 keV, it is 10 power minus 17, and from 1 if I go to 2, it is 10 to the power minus 14, from 2 if I go to 5, it is 10 power minus 10. So, initially this sigma v increases with temperature, but if you increase the temperature beyond a certain limit, it goes to very high values. So, I am going to the board now for 2-3 minutes. So, this product you have seen, a to this exponential and this exponential, and one exponential just drops like this. This is the e to the power minus e by kt, and this rises somewhere like this, and so it is this region which contributes, and the product goes like, it goes through a maximum, and it is this area, it is this integration that gives you sigma v, which depends on temperature. Initially this sigma v here, temperature, initially it increases, and then if you increase the temperature to very high values, it will start taking a downward trend. So, using these kinds of things, one can calculate the reaction rates. Of course, the concentrations are needed. So, one can calculate the reaction rates for a given concentration, what is the rate for different nuclear species. So, it turns out that for low Z nuclei, which we are interested in if we have to design a thermonuclear reactor. So, for low Z nuclei fusion, which for Coulomb barrier has to be low, this deuteron plus triton 2H plus 3H, this has the best D plus T. Okay. This is 2H and plus this is 3H. This particular reaction has the best possibilities. So, we will talk more about it in the next lecture. What kind of considerations are there to design a thermonuclear fusion reactor, why it is not yet commercially available, why scientists are taking decades and decades of research and still are not coming up with a feasible design which can give us power from nuclear fusion. All these topics in the next lecture.